Hello guys, welcome to Yebo Physics on a Wednesday afternoon. I hope I find you well. So as you may have seen from the title of the stream or from the communication sent earlier, we are going to be looking at questions on sources of magnetic field. That's what we want to look at. So feel free to interact with me and feel free to interject me at any point when we're solving the problems. So I'm already showing a question on the screen there, which is question 9 from the tutorial. So that's question 9. Okay, and that's the first question that we're going to look at today. So the question says, in the figure shown, what is the magnitude of the magnetic field at point P? express your answer in terms of mu naught, the radius A, radius B, and the current I. Okay, so that's the diagram that we're given there. It's clear, well represented and annotated. So remember, when dealing with sources of magnetic fields, we should recall our Ampere's law, integral of B dot ds equal to mu naught I. So I'm just writing down mdb equals to mu naught I over 4 pi r squared integral of dl, okay, which is the length of arc. So remember, probably from the derivation in class, that straight line do not contribute to the magnetic field, right? So straight lines do not contribute to the magnetic field, which means we're looking at only the curved surface or the curved sections of that conductor. Okay, so now having said that, we can see that from the curved surfaces we've got two curved sections, where the smaller sections where we've got a radius of A, then the larger section we've got a radius of B. Okay, which means that we have got two sections of the wire that are contributing to the magnetic field at point P. Okay, and the total sum is a contribution to that particular point P, right? So which means that to determine the magnetic field, we need to determine the magnetic field as a contribution of this part of the wire, which is this part, and also due to this part. Okay, and remember that these straight surfaces do not contribute. So which means that B total will be equals to BA plus B of B. Now we've broken down the question. Now what remains is for us to solve. So which means we have to find BA and also find B of B. Okay, then we sum the two together. And we're going to be using our equation. All right. Now let's solve. Starting with BA. Okay. So we can say dB of A is equal to mu naught I over 4 pi A squared, which is the radius, integral of dl, which is where L is the length of the curved section of the wire. All right, and then from there, simplifying, our B of A will be equals to, if you integrate both sides, that will be mu naught I over 4 pi A squared. And the length of arc, we know that for a complete revolution, L is equals to 2 pi r for a complete revolution, right? But if you look at what we have in this case for A, this is just a quarter of a circle, okay? It's just a quarter of a circle. You can see by the angle there, this is just 90 degrees. So that's a quarter of a circle. So which means it's going to be a quarter of 2 pi r, okay? So that will be 2 pi a divided by 4, okay? Because it's a quarter, right? Then you can cancel like terms. You can cancel that. You can cancel that. You can cancel that a. You can cancel that 2. And then you remain with your BA being equal to mu naught I over, it will be 8 there, but 2, so that's 4 mu naught I over 4a. Right. 4 times 4, 16 over 8. Yeah, 4 times 4, that's 16 over 8a. Over 8a. So that is what I'm getting for BA. Okay, this is for BA. Now let's work out for the larger radius. Okay, let's work out for the larger radius. So the larger radius is going to be BB equals to mu naught I over 4 pi b squared times the length of the arc. This time you can realize that this is actually 3/4 of a circle, okay? Which means we've gone all the way and we've gone 270 degrees, and that is 3/4 of the circle. So that is going to be 3/4 of 2 pi b. Again, we cancel like terms, cancel that, cancel that. What else? Okay, leave it as it is. So b of b is going to be equals to mu naught I over, that will be 8 divided by 2. That's okay, that's 16 divided by 2. That's going to be 8. So that's 3 over 8a. Okay, that's 3 over 8a. If you do the maths there, then like I in not a, it's b. Okay, where am I saying? It's b. Okay, so like I had indicated earlier, the b total will be the sum of the two. Okay, it'll be the sum of the two. So that's going to be BA plus B of B. So that is going to be BA, which is mu naught I over 8A plus 3 over 8 mu naught I. Okay, so you can factor out, that's mu naught I over 8 factored out, remain with 1 over A plus 3 over B. Okay, so now this is just simply you're now just simplifying, right? Okay, so this will be mu naught I over 8. Our common denominator there is going to be a b, remain with b. Remain with b there. That becomes b plus 3a. Right, so this is what I get for the b total. Right, let's see what are the options that we have there. B plus 3a, b plus 3a over ab, b plus 3a over ab. Yeah, that's what I get. So that is the option there. Okay, I hope you would get the same when you try it on your own. So that's number 9. So basically we just used this equation, the Biot-Savart, and remember that straight lines do not contribute to the magnetic field. And then you look at the curved sections of the conductor and solve for BA, solve for B of B, then get the sum, which is the total. Now let's move on to question 10. Question 10. What is the magnitude of the magnetic field at point P if A is R and B is 2R? Okay, now we have got a different situation there, right? So, but again, we're still using the same equation to solve, because we did determine earlier that to determine our B total, B due to A plus B due to B. All right, this is what is going to guide us. All right, and also remember that your dB is equals to mu naught I over 4 pi r squared integral of dl, right? So we can see that for both radius A and for radius B, the angle there is 360. So which means that all that is 3/4 of the circumference, which is 2 pi r. So it's going to be 3/4 of 2 pi r. But now one thing that you should notice is that the direction of current is different, right? For the radius of B, the current is going in a clockwise direction, but for radius A, the current is going in an anti-clockwise direction. Okay, which means that one of the magnetic fields is positive and one of them is negative. All right, so we're going to start with B of B, which is the larger radius. Okay, so basically this is going to be B of B being equals to mu naught I over 4 pi. The radius squared for B, okay, or let me just say B squared times 3/4 of 2 pi B. Okay, now let's simplify mu naught I over 4 pi. But remember, B were given as 2r. Okay, so if you substitute there 2r, that will be 2r all squared multiplied by 3/4 2 pi to are. Okay. But I guess we can, to make it easier, we can simplify at the end. That's what I'm thinking now. We can simplify all this, leave it in terms of B. I think that will be easier. Leave it in terms of B until we substitute at the end. I think this should still work for us. Yeah, it'll be easier. Let's first simplify. Well, this is another way of doing it. You can do it anyhow. It will still give you the same answer. But just for simplicity, this is just for simplicity. I'll leave it in terms of B. Okay. Then I'll cancel this B, cancel the square, cancel the pi, cancel that. And then if I continue, B of B is going to be equal to mu naught I. You've got your 3 there. 4 times 4 is going to be 16, divided by 2 is going to be 8. 8b, right? So that is what we get. This is the magnitude. But now to determine the direction of the magnetic field, now remember I said on one of the conductors, it's going clockwise, one of them is going anti-clockwise. So you can use your right hand grip rule. That's right hand grip rule, where the 4 fingers are pointing in the direction of flow of current. Okay. Then the thumb is pointing into. Okay. So if you align with the sketch, you'll see that the thumb will be pointing into the page, right? And into is negative. Okay. So this is going to be negative because the thumb is pointing into the page. Okay. I hope you're able to use your right hand grip rule. So the thumb will show you the direction of the magnetic field. The 4 fingers are showing the direction of flow of current. So if your 4 fingers are in the direction of flow of the current, okay, okay, perhaps you can't see. It's going to be a bit difficult to illustrate this, but your thumb shows you the direction of the magnetic field. Your 4 fingers are pointing in the direction of flow of current, right? So if you align with the direction of flow of current shown for the radius B, for the current flowing in the semicircle B, then it means that your thumb is going to be pointing into P. Okay, and that into shows a negative direction. All right. Now let's do for B of A, magnitude to A, which is going to be mu naught I over 4 pi A squared, and this is going to be 3/4 of 2 pi A. Okay, we do the same thing. We cancel there, cancel there, cancel that, cancel that, and see what do we get. B of A, it's going to be equals to mu naught I, so 3 there, all over 8A. Okay, so what differs now is the value for A and the value for B. All right, so remember, say the B total is going to be equals to BA plus B of B. Okay, but our BA, okay, our BA is 3, which is positive. All right, but so we can see that the direction of current is flowing in the opposite direction, which means that the direction of the magnetic field is going to be the opposite. You can still use your right hand grip rule still to confirm. So now if you use your 4 fingers to align with the direction of flow of current, which is going anti-clockwise, you'll see that the thumb will point towards you or out of the page. Okay, which is exactly the opposite with when the current was flowing in a clockwise direction. So this means that the magnetic field is positive. So this one is positive. So which means that here to get our sum of BA is 3 mu naught I over 8A. Okay. Minus, because we said B of B is negative, minus 3 mu naught I over 8B. We can factor out 3 mu naught I over 8, I mean 1 over A minus 1 over B. Okay, then we can substitute now the values for A and the values for B. The value for A, it's R minus 1 over 2R. And we're leaving this in terms of what? In terms of, okay. So still we can factor out, we can continue to factor out, so that becomes 3 mu naught I over 8R. It's going to be 1 over 1 minus 1 over 2. So it's going to be 1 minus half, it's going to remain as half. So it's going to be 3 mu naught I over 8 times 2, which is 16R. So that becomes our B total. Okay, so that's how we go about this particular question. So it's just similar with the first question, but now because the direction of currents were in opposite direction, which means the direction of the magnetic fields also are going to be different, but we're still summing the magnetic field. Okay, now let's move on to question 12. Is it question 12? No, 11. Okay, let's see how this looks on the page. That's fine. Okay. Right, so question 11 reads, with question 11, what's question? Let's see, let me just confirm out on this. 10. Oh, so we're doing question 11. All right. So that's 11. Okay, so I'm going to read the question. It says the figure shows a cross section of 3 parallel wires carrying a current of I. A current of I. The currents in wires B and C are out of the page, as you can see. B and C. We've got represented by dots there, which means they are out of the page, right? And then for A, we can see that it's a star, so it's into the page. So the distance between each wires is indicated. What is the magnitude of the force per unit length on wire B? Express your answer in terms of mu naught, R, and I. Okay, so now we have to think of which equation are we using in that case now. Just going to scroll here. Okay, that's fine now. Right. Okay. Now I've got enough writing space. So question 11. was going to put that sketch there. So this is 2R and this is R. So this is A, this is B, and this is C. Okay, so remember F is equals to pi L sine of theta. And for a straight conductor, this will be your B. Your B will be mu naught I1, I2, L sine of theta, okay, all over 2 pi r. I'm sure you've used this equation in class, right? That's for two parallel conductors, okay? Now, if we look at this situation, we're looking at the resultant magnitude of force per unit length on wire B. Okay, so we can change this. It's going to be F over L, which is equals to mu naught I1, I2 over 2 pi r. So since the wires are parallel to each other, the magnetic field will be perpendicular. So sin 90 will give you 1. Now, let's see the direction of forces which are going to act on B as a result of A and C. All right. So between A and B, these are two conductors carrying current in opposite directions. So we expect a repulsion. Okay. So we expect A to move this way and we expect B to move that way. For A and B, it's a repulsion. Two conductors carrying current in the opposite direction, they should be repulsion. Now let's see for B and C. For B and C, two conductors carrying current in the same direction, we expect an attraction, okay? Which means C will go in this direction and B, oh, no, not that way. If it's an attraction, C will go in that direction, but B will move to the right. So which means that the effect of this situation on B will result in B moving to the right or towards the right. Okay, so that is what we are concerned about. Okay, so now we see that well, considering to the right, it's going to be positive, right? So it's going to be our force being equals to force of A on B plus force on C, force of C on B, right? So F is going to be equals to, so it's already force per unit length, okay? So it's going to be this equation that we've highlighted here, okay? But in this case, that these conductors are carrying a current of I, all of them, okay? So which means that this becomes mu naught I, instead of I1, I2, that becomes I squared, all right? Over 2 pi, the radius, which is 2r, plus mu naught I squared again over 2 pi r, the radius. So if you simplify that, that becomes mu naught I squared over 2 times 2, that's 4 pi r plus mu naught I squared over 2 pi r. So you can factor out mu naught I squared over pi r, so it's 1 over 4 plus 1 over 2. Is a quarter plus a half to give you 3/4. Okay, that will be 3 mu naught I squared over pi r. So that's your force per unit length, 3 over 4 pi r. Okay, so that's how you go about such a question. All right, 3 over 4 mu naught I squared over 4 pi r. Okay, so let's see. All right, so let's move on to question 12. If there are no queries on that one. Okay, there is our question. All right, so this is now question 12. So what does the question say? The figure shows a cross section of 3 parallel wires carrying a current of I. The currents in wire A and B are out of the page, while that in C is into the page. What is the magnitude of the force per unit length on wire A? Okay, so now we're considering wire A. So we could put an axis on wire A if we want. Okay, so A is our reference, like I was saying. A is our reference. And the force on A is going to be due to the force C on A and C on B. Okay, but now here you see that these conductors you would need to resolve, okay, because of how they are arranged. It's unlike the previous question where they were just in a straight line. So we can put an axis here at A. Because we're looking at our reference A, okay? Now, because this is an equilateral triangle, obviously this is 60, 60. That means that this is 30 and this is 30, okay? Right, before we go that far anyway, let's determine the forces that are going to act on A, right, due to B. So for due to B, we see that the direction is going out of the page for both A and B. So which means that these two conductors are parallel and are carrying a current of they're carrying a current outward, which means that there's going to be an attraction, right? There's going to be an attraction, which means that B will have a tendency to move that way, whereas A in this direction. Okay. And then how about due to C? So it's going to be a repulsion. C would move in this direction, or the and whereas at this point the force would be in this direction. Okay. All right. So with our analysis, this is obviously going to be 60, right? This also 60, and this here is 30. Okay. So if you draw a reflection of this equilateral triangle and do these angles, you will realize that, or rather, if you want to check, this would be a reflection of the same triangle. This is how it would be. This becomes a 30 there, okay? And which means that this angle 60 there and 60 which I've indicated there, okay? But that's just to clarify in case someone is wondering how we come up with the angles, but I'm sure it's quite clear. So these are going to be the magnitude of the forces. Force F, right? So the force on A is going to be due to F in the vertical plus F in the x-axis, because you can see that these forces are at an angle, right? Now, if you look at Fy and you are resolving along the y-axis, okay? If you are resolving along the y-axis, for example, if you close and have a right angle triangle there, if you resolve along the y-axis, that is going to be equals to a positive F cos 30, okay? And if you resolve on the negative y-axis, this is going to be negative F cos 30, which means F in the y is equals to a 0, okay? Which means that the only contribution for Fa is going to be equals to F in the x, which is entirely on the negative x-axis, all right? So F on A, okay, F on A, it's going to be equals to, which is our F on X, it's going to be equal to, now we're resolving along the x-axis. If you close there, you have a right angle triangle, right? So it's going to be negative F cos 60 minus F cos 60. So which means your Fa is going to be equals to negative 2F cos 60, right? But remember, we're looking at the magnitude of force per unit length, right? The magnitude of force per unit length. Yeah, which is what we have already used before here, which is this, right? and the currents are the same. So it's going to be -2. So now this is now F per unit length, so it becomes M mu naught I squared over 2 pi r cos of 60. In case you're wondering, it's this equation that we've just taken and substituted. Remember, the I1 and the I2 are equal, so it becomes I naught squared, I squared rather. So the force per unit length there becomes 2, and that 2 cancel out. You remain with mu naught I squared cos of 60 over pi r. Okay, we've ignored the negative because the question is only asking for the magnitude. Mu naught over pi r, sine is out, mu naught I squared over pi r, so it should be so that is what we get. All right, so it's just similar to the previous question, but only in this case that these conductors now, they are still parallel, but they are not in the same line. Okay, you did a lot of resolving last semester, so that should not be a challenge to you at all. Now let's look at question 13. Question 13. So question 13 reads, as shown in the figure, the current as shown in the figure, the current in the long straight wire is 5 amp. The wire lies in the plane of the rectangular loop, which carries a current of 1.2. No, which carries a current of 10.0 amps. Is it 10.0 or 1.0? Okay. It's 10.0, yes. 10.0. The dimensions of the figure C equals to 0.1 meter and 0.150, and the L is 0.45. What is the magnitude and direction of the net force? Okay, so we need the magnitude of the net force exerted on the loop by the magnetic field created by the wire. Okay, so I've already shown I'm already showing the diagram there. C, I'm going to put the magnitudes here. C 0.1, and then for A 0.15. Yes, 0.15, and C plus A from there to there, it's going to be 0.25 meters. Okay. All right, so now we know that between any two straight conductors carrying current in the same direction, there's going to be force of attraction, and if they're carrying current in an opposite direction, there's going to be a repulsion. Okay, so for I2, we can see that current is going upwards like that on this side of the loop, which means that on this other side of the loop, current will be going down. All right. So, which means that the straight conductor acting on the loop will be influenced by the left side of conductor on the loop and the right side of the loop. Right? So which means that if you are to come up with an equation, it means that your F net will be equals to the force due to the left side of the loop plus the force due to the right side of the loop. Okay, so now the force due to the left side of the loop, we see that this is going to be an attraction, okay, between these two. So for the left side, between the conductor and the left side, we can see that the current is going up, so we expect an attraction, okay, which means that this conductor would move in this direction, and this loop would move in this direction. Okay, so which means the force of the straight conductor on the left loop, FL, will be to the left, FL. Okay, then if we consider the straight conductor again, which is this one, and the right side of the loop, we see that the current is moving in opposite direction, so we expect a repulsion. Okay, which means that this should move to this side, and this should move to this side. Okay, so which means the force of the straight conductor on the loop due to the right side will be moving to the left. Okay, which means that our FL, because it's moving to the right, it's going to be positive. Then our FR is going to be negative, because there is a repulsion between the straight conductor and the right side of the loop. I hope this makes clear. All right, so the force now can be summed up easily. All right, so FL is positive, so F net is going to be equals to mu naught I squared, because the magnitudes are they the same? No, they are not the same. So this is going to be, I think I should write this down here for space. F net is going to be mu naught I1 I2 over 2 pi r, which is the distance between these two conductors. Okay, am I right? FL, yes, which is C. Okay, so we'll call it C, minus, because FR is negative, so that becomes mu naught I1 I2 over 2 pi r. Now the distance from this conductor to this conductor, C plus A, okay, which we determined is 0.25. Okay, so having done that, now you can factor out what is common, mu naught I1 I2 all over 2 pi 1 over RC, it's okay, minus 1 over RCA. So that becomes, now we can substitute mu naught 4 pi times 10 to the negative 7 times our current, which is 5. Our current is given as 5, yes, and the other one is 10. Oh, I left out the L, the length of the conductor. Length of the conductor, which is 0.45 over 2 pi and 1 over RC is 0.1 minus 1 over RCH is 0.25. Okay, then you can punch that. So you can punch along to see if what I'm writing is consistent with what you're getting. One over 0.1 minus 1 over 0.25. So you get 2.7 negative 5 newtons, okay, which is the same as 27 times 10 to the negative 6 newtons, and this is 27 micronewtons. Okay, now you can carefully analyze the direction. What do you think the direction would be? Is it to the left or to the right? So now look, our FL so I was saying, which direction do you think that coil would follow? Because look, listen to the question. It says, what is the magnitude and the direction of the net force exerted on the loop by the magnetic field created by the wire? So meaning to say, in which direction is that loop going to move? Will it move on to the left or will it move to the right? What do you think? Would it move to the left or would it move to the right? Left or to the right? Let me see if there are any comments that are coming in. Do you expect it to move to the left or to the right? So according to what we have just shown you there, right? We expect that the net force exerted by the loop on the magnetic field created by the wire should move to the left, right? It should move to the left, which is to the negative x-axis. So it will be pulled towards the left side where the force is greatest, right? It will be pulled towards the left side, which is the negative of the x-axis. So the magnitude, you're simply following your calculations that we've shown you there. Okay. And then for direction, you're simply looking at the your illustration there and the force acting on the system, right? To determine the net direction of, not the net direction, but just the direction of the net force exerted on the loop by the magnetic field created. Okay. So let's see if we've got definitely not out of the page. So that's not 54. So that's along the negative x-axis. Why? Because we are saying if due to, so if I'm to explain that in case you're wondering, that the magnitude of FL the magnitude of FL is greater than the magnitude of FR. Okay. Why? The inverse square law. Look at the radius. Look at the radius. So for FR, the radius is larger. It's CA, which is 0.25. But for FL, the radius is C, which means that the radius C is lesser than the radius CA. Okay. And due to the inverse square law, for F is equals to mu naught I 1 I 2 L over 2 pi R. So we're saying for FC, we can see that we've got a smaller radius, okay, which means FL is going to be greater, okay, which means that that's why we're saying FL is greater than FR. So which means that the pulling effect towards the left side on this loop FL is going to be greater than the movement to the right, this FR, okay, which means the movement to the left would be greater than the movement to the right, just because the magnitude of the forces are not equal, okay? The magnitude of the forces are not equal. The magnitude of FL is greater than the magnitude of FR. All right, so that is it. So I hope that makes sense. Let's move to question 14. Question 14, and just scroll there. So Gauss' law states that the net electric flux through any closed surface is proportional to the charge enclosed, which is that. The analogous formula for magnetic fields is, so for magnetic fields, remember that B dot dA is equals to 0. And what does that mean? The net flux through any closed surface is 0. Okay, so this is just revision for the chapter 27 or chapter 28, what you did earlier. Hopefully you haven't forgotten that. Okay, let's look at 2 more questions. Question 15 reads, a long cylindrical radius 2 centimeters carries a current of 40 amps that is uniformly distributed over a cross section of the wire. What is the magnitude of the magnetic field at a point which is 1.5 centimeters from the axis of the wire? Okay, excuse me. Okay, so this is 2 centimeters, okay? But we are being asked at 1.5 centimeters, okay? So at 1.5 centimeters, what is the magnitude of the magnetic field at a point which is 1.5 centimeters from the axis, right? So what happens to the magnitude of the current as you move further from the axis? Does it increase or decrease? So if you recall, your equation I is equals to A N Q V for current flowing in a conductor, where A is the cross-sectional area. So current is directly proportional to the area, and which means that your current is directly proportional to pi r squared. Okay, which means as you increase the radius, the current also increases. Okay, as you increase the radius, the current also increases. So which means as you decrease the radius, the current also decreases, which means the current at 1.5 should be lesser than 40 amps. Okay, that's what essentially it means. All right, so in this case, we're looking at a case where r is less than the radius. Okay, which implies that the current at 1.5 is less than the current at radius I, at 2 centimeters rather. Okay, so that's one way to put it across. All right, so let's see how these two currents relate. Okay, let's see how these two currents relate. So for I1, which is equals to pi, small radius less than the actual less than 2 centimeters. Okay, and put it as a ratio for I, which is pi r squared. Okay, so which means that the current at 1.5 centimeters will be equals to r squared over r squared times your I. Okay, now we can recall, now that we have got the current at 1.5 centimeters from the axis, we could consider using the equation B dot ds equal to our b times length of circumference, which is, know that is also equals to mu naught I1, right? And now that we have determined our mu naught, now that we've determined our mu naught, our I, actually our I1, so this equals to R squared over R squared times I left my mu there, so this becomes mu R squared over R squared times I. Okay, something like that, right? So which means you can now equate this and that, right? So that becomes your b 2 pi r equal to your mu naught r squared over r squared I. Okay, and you can find your b now, your magnetic field b, which is what we're looking for. B equals to, okay, you can cancel that, cancel that. So that's b equals to mu naught I r over 2 pi r squared. Okay, and this applies as magnetic field for whenever the radius is less than the actual radius. Okay, now value for mu naught, okay, so we can use 8.85 times 10 to the negative 12 times the radius, which is 1.5 times 10 to the negative 2, because it's in centimeters, over 2 pi times 2 times 10 to the negative 2 all over squared, all squared rather. Then we can punch this to see what we get. Also punch along to see. The value I'm getting here, I'm just going to extend this so that you can see. I left the I there. What is the current? It's 40. Okay. value that I'm getting is too large than I expected. Could I be missing something? 2 pi r squared. (1.5 times 10 to the negative 2). And there's nothing of that sort. Let's see. 8.85 times 10 to the negative 12 times 1.5 times 10 to the negative 2. Let's do this. 4 pi times 10 to the power of negative 7. Yeah, that is my mistake there. Otherwise, that's 3 times 10 to the negative 4 Teslas, which is the equivalent of 30 times 10 to the negative 6 Tesla, which is 30 millitesla. Right, I hope you also get that when you punch that. Any questions or comments in the chat? I don't see any. I don't see any questions, comments, or contributions in the chat, so we're going to proceed to the next question, which happens to be the last question. So this is question 16, the last one for the day. Okay, just a moment. Right, let's move on. A long wire is known to have a radius greater than 4 millimeters, and to carry a current uniformly distributed over its cross section if the magnitude of the magnetic field is 0.285 millitesla at a point 4 millimeters from the axis of the wire and 0.2 milliteslas at a point 10 millimeters from the axis. What is the radius of the wire? Okay. Right, so I'm going to write down the information given. So we're told that the radius is greater than 4.0 millimeters. Then we're told that at B, okay, the B, or the magnetic field at 4 millimeters, it's equals to 0.285 millitesla, and then B at 10 millimeters, it's going to be 0.20 millitesla. Okay, so from what we did in the previous question, you recall that the B is going to be equals to B 2 pi r is equals to mu naught r. Okay, so if you would do for the radius at 10 millimeters, B at 10, 2 pi, and your radius at 10 will be equals to mu naught I, right? And specifically what we are told about the wire, it has got a radius known to have a greater, the long wire is known to have a radius greater than 4 millimeters. Okay, so if it's 4 millimeters, if it's greater than 4 millimeters, which means r at 4 is less than the radius. Okay, so which reminds us of what we worked out in our previous question to say if our radius is less than the actual radius, then this is our value for our B. Okay, B is equals to that. Okay, so which means that this is information that we could make use of, right? This information that we could make use of from the previous question, actually from here. Okay, if you understood how we arrived at this point and how we solved the previous question, then you know that you're taking this information to the next question. So it's going to be B 2 pi r equals to mu naught r squared small r over the larger radius multiplied by your I. Okay, so that will be 2 pi r B 2 pi r B 2 pi r equals to B 2 pi r equals to mu naught I r squared over r squared. Okay, and then then obviously you would have to equate. Hope I represented this correctly. Let me just check, just confirming B from the previous question. All right, so this will actually be for B less than that will be your B4. Now in terms of, I've just putting it in terms of B, your B4, which is your 2 pi r squared over r4, which is equals to mu naught I. Then from there you can equate the two equations together. So I've just rearranged what we had earlier on. Okay, so equating the two, since it's all equals to mu naught I, that will be your B10 2 pi r10 equal to your B4 2 pi r squared over r4. Okay, so we've just made mu naught the subject of the formula from what we did in the previous question. Okay, so in case you're wondering, from this stage we just make mu naught I the subject. So we just made mu naught I the subject, so we remain with B4 2 pi r squared over the radius 4. So that's what we did. So we did not derive it again, just for purpose of time. Then you can cancel out, that cancels out, that cancels out, that cancels out. So you obviously, because you're looking for r squared, it's going to be B of 10 r of 10 over r of 4. Okay, and r will be obviously a square root of a B of 10, which is 0.2 times 10 to the negative 3 times the radius B of 10, which is 10 millimeters. 10 times 10 to the negative 3 times I think I missed something here. Just a moment. Go back to this simplified r squared. It's going to be B of 10 r of 10 r of 4 over, I had left B of 4. Okay, so your r is going to be equal to the square root of B of 10, which is 0.2 times 10 to the negative 3 times 4 times 10 to the negative 3 times 10 is 10 to the negative 3 over B of 4, which we're told that it's 0.285 times 10 to the negative 3. Now you can punch along. So that's 5.29 times 10 to the negative 3 meters, which is the same as 5.3 millimeters. So this is how you'd go about this particular question. So you'll see that there is a link between question 16 and question 15, and they've been ordered in such a way that you can relate with the two scenarios that were presented. So this is what I for today's tutorial. I can see a number of people missed the tutorial, maybe due to lectures or some other commitments. However, please do find the recording of this tutorial on the Yebo Physics YouTube channel. Okay. Nkutazo, I can see you joined just a while ago. I hope that you would be able to go through the recording and see if you can follow the questions on what we're doing on sources of magnetic fields. Will you be able to do that? I hope so. I hope so. All right, so this is what I had for today's tutorial, like I had indicated. So there are more questions on sources of magnetic fields. So be sure to join in the next tutorial. We're just going to be covering question 17 up to the end of the tutorial questions up to question 25. You can try out these questions well in advance. Then during the tutorial, the tutors will be there to guide you. So I wish you the best in your studies, and from me and everyone else in the studio, it's a goodbye.